In this video, we are going to learn how to compare two variances of two different samples. So we are going to interpret F distribution, understand what means F distribution, F table, to find critical value, perform a two-sample F test to compare two variances. Okay. Let's understand first what is F distribution. F distribution is also, first of all, it's known as a Fisher distribution. Let me take. It's also known as Fisher distribution, F. It's extensively used to test for equality of variances from two normal populations. Okay. So F distribution curve is skewed positively because based on formula, see we have here S1 squared, S2 squared, because it's squared, so it will never go into negative area. It's always going to be between 0 and positive infinity. Okay. So it's gonna test based on F distribution. It's gonna test on equality of normally distributed populations. Okay, but we are, as always, we use their sampling, right? Which is we are going to use the variances of samples, which is S2, right? Okay, so let S1 squared and S2 squared represent the sample variances, sample keyword variances of two different populations. If both populations are normally distributed and population variances are sigma 1 squared, and here should be sigma 2 squared, and they are equal, then sampling distribution would be equal. F is equal S1 squared over S2 squared. Okay. So when we should use F distribution, how to know when to use F distribution? So F distribution we use when we are testing on equality of variances between two samples, or which means between two populations. As we said, based on formula, F is equal sigma 1 squared over sigma 2 squared. Okay, F distribution is a family of curve, each of which is determined by two types of degrees. Degree of freedom corresponds to the variance in numerator. Degree of freedom in numerator, which one is going to be for this one. And then degree of freedom corresponding to the variance in the denominator, since we are testing two variances, right? Non-inequality. So degree of freedom for sigma 2 squared. And I already mentioned that F distribution is positively skewed. It can be only from 0 to positive infinity. And the total area under the curve of F distribution is equal 1. So the total area is equal 1. So here it's showing the graph already, so properties of the F distribution. So what we can say about properties of F distribution. So F values are always greater or equal than 0, like I said, between 0 and positive infinity. Between 0 and positive infinity. For all F distribution, the mean of value F is approximately equal 1 because it takes 100%, right? Next, f value of f can never be negative, and the shape of distribution depends on degrees of freedom of numerator and denominator, because f value, we said it's a the sigma 1 squared over sigma 2 squared, or s1 squared. It also can be s1 squared over s2 squared. So from this graph we can say that the degree of skewness decreases with increase of degrees of freedom of numerator and denominator, right? So the greater than degree of freedom for numerator and denominator, the lower is the skewness. Why? Because mathematically, when we are looking, they are inverse proportional. And f distribution curve never is symmetrical. So f test that represent the test of f distribution compares the more than one level of independent variable with multiple groups within f distribution. So why do we compare even with multiple groups? To get close to the truth answers. Okay, just like from elementary statistics, if you remember, to get, if we have large sample size, large sample, we take several the groups, and then we find x bar from each one of them, right? And then we take average of the average of for all those all these groups to get close to the real value. Okay, but in the case of f distribution, f test, it's used like in ANOVA calculation, which is testing usually. It's testing equality of variations between samples. So always use f distribution for f test to compare more than one groups. So to assume the f distribution, we always assume that both populations are normally distributed. Both populations are independent to each other, and the larger sample variance always goes in the numerator. So how do you know, let's say you have two samples, how do you know which one to take S1, which one you take S2? The larger sample variance always goes in the numerator. Okay? It always goes in the numerator. This is for larger samples. So larger sample is taken as a S1 in numerator, and small one goes to denominator. So the larger sample variance always goes in the numerator to make the right-tailed test, and the right-tailed tests are always easy to calculate. So this is why this our f distribution, you see, it's a right-tailed test. This is why we always make sure that we get right-tailed test, and we will get right-tailed test if the numerator will be greater than denominator. Okay. So we said that, or I said that f distribution, is equal sigma 1 squared over sigma 2 squared. So how much is sigma? How we calculate sigma? This is variance, right? Sigma is equal sum of sigma squared, variance is equal x minus mu. This is from normal distribution, we know this, divided by n. This is from elementary statistics. I just refresh your memory. So you can calculate this way. So to find whether two independent estimates of population variances differ significantly or insignificant, and we can accept it as variances are equal. Or to find out whether two samples drawn from the normal population, we are going to use in that case f is equal s1 squared to s2 squared. Let me repeat myself so you would know when to use what. So if we want to find out whether two samples drawn from the normal distribution, from the normal population, having the same variance, we are going to use this formula because we are going to use sample variances. Okay? But if we want to find out whether the two independent estimates of population variances differ significantly, then we are going to use this ratio. Okay? So, like I said, F statistics, also known as F value, and like I said, it used not only ANOVA but regression analysis also to identify the means also, not only variance but the means in the case of regression. So to identify if the means between two populations are significantly different or not. So shortly saying, F statistics is a ratio of two variances. And remind you, what is variance? Is nothing but measure of dispersion, right? It tells how far the data is dispersed from the mean. So, and F statistics account corresponding degrees of freedom to estimate population variance. F statistics is very similar to T statistics, with the difference. T-test states a single variable that is significantly, statistically significant or not. Okay, one single variable. F-test test states a group of variables that are statistically significant or not. Okay, and the F statistics are based on the ratio of mean squared. So, let me see. F statistic is a ratio of mean squared for treatment or between groups with mean squared, for error between groups. Let's say here with our population, and we are taking several groups. Okay, it's using the mean squared, meaning errors between these groups, how they affect each other, shortly saying. All right, that's what it is. And we say it's an F that is equal MS mean square between groups. MS is within. Let me see. MS is, we are looking for mean square for a variable within the group. So within and between the group, because we have more than one variables, right? Okay, so let's see how it's gonna work. So I will come back for critical values, but I would like to write down as of now the what I want to say. So it is very important about right tail, left tail, okay, and two tails. At this point, let me write down. So, if alternative, I'm going to use, because it's going to be hypothesis test, so if alternative hypothesis, sigma 1 squared, since null hypothesis is always going to be equal, right? Sigma 1 squared is equal sigma 2 squared. Now I'm going to look into versions of alternative. Sigma 1 squared greater than sigma 2 squared, okay, then we have right tail. If sigma 1 squared less than sigma 2 squared, we have left tail. If sigma 1 squared not equal sigma 2 squared, we have two tail. Okay? All right. In the case of right tail, so if f is greater than f, our the statistics, then we're rejecting. So let me write down rejection area. So for right tail, f has to be greater than f alpha. For left tail, f has to be less equal than f1 minus alpha. I'll explain all this. And then for two tails, f less equal f1 minus alpha half. Okay, or f greater equal of f alpha half. Okay, now let's go back. So what do we need to do? So to be able to do f test and then compare rejection region, no rejection region, fail to reject region, as we already know, we need to have the critical value, right? So for critical value, we need to take our significance level alpha, determine degree of freedom for numerator. It's going to be n minus 1, n1 minus 1. Here it's going to be n2 minus 1, right? And then we are going to use table. I'm cleaning here, so to make sure we are not looking for table 7, because this is just from somewhere else. We are going to find the critical value f. We can look for f table. Hold on. So find the critical value. If hypothesis test is one tail, then we use alpha f table. If we have two tail, then we are using alpha half from f table. Okay, so here is the table, finding critical value, critical f value. So that's a critical f value for a right tail test. When alpha equal, here we have 0.1, 10%, and degree of freedom for numerator is equal 5, meaning for the first test. And second one, second sample, it's going to be 28. How we are going to do, as we know, we take, because they are paired, because they affect each other. So from, just like in the t-test, we used the degree of freedom for the smaller sample size, right? In our case, smaller sample size is how much was since degree of freedom 5, we had 6 and 29. Let me see. No, it doesn't tell us. It just take the number. Okay, that's fine. So if that means degree of freedom is if 5, that means n is 6, and if degree of freedom of denominator 28, That means n is 29. So we are taking the degree of freedom 5, degree of freedom for smaller sample size, right? And we are taking 28 degree of freedom. This is for our denominator. So this is numerator. Here we have 5, here we have denominator. And for alpha is equal 0.1, and intersection will give us critical value for 2.06. Okay, all right, next one. So here is example. We are going to find critical value for alpha 0.05. Degree of freedom for numerator is 4. Degree of freedom for denominator is 8. But here we have for two-tails test. Okay, so for two-tail test, when we are using F distribution, so we need to find the right tail, because F distribution shows the right tail, right? So which means if our alpha is 0.05, we are going to split. We have only here one tail, so we split, we get 0.025. Okay, in the case of two tail, as always we split it, right? Okay, so let me zoom it. When we have critical F value for 0.025, here is our 0.025, and degree of freedom, let me go back here, a degree of freedom 4 and 8 denominator. So for numerator is 4, which is numerator is going horizontally, for denominator is going vertically. So we have 4 and 8, and we take interception for these two. It's going to be 5.05, and that's going to be our F critical value. Okay, so two sample F test for variances. To use two sample F test, we were learning now how to calculate the critical value for F. Now let's start doing F test for variances. So conditions that we can, when we can use F test, I already mentioned, but we go one more time. It must be randomly selected, samples must be independent, and each population must be normally distributed. Two sample F test for variances. So TestStatistics is equal S1 squared divided by S2 squared. S1 squared, S2 squared, it represents sample variances. I already mentioned, and S1 squared always, let me write down one more time, S1 squared always has to be S2 squared. How we achieve that? Well, by choosing larger population has a greater variance, right? And why we choose specifically greater, not less, because we are going to, it's easy to work with F test of the F distribution with right tail test. Why? Because right tail test is always going to be positive, and we are working with squares, which is everywhere it's positive, right? So the degree of freedom for the numerator is n1 minus 1, where we know it's matching to variance S1 squared. Degree of freedom for denominator n2 minus 1, so having variance S2 squared. Okay, so here is going step by step what need to be done. You can read it by yourself later on. I don't need to just read it. I rather show you in example how to solve it. So it's they say it's better but the 1 times to C, then 10 times to here. So what happened? Oh, here it is. This one has to be wrong one chose. Okay. All right. So I'm going straight to example. The only thing I would mark down here, so if although I already mentioned, but just in case, it will never hurt to repeat. So when our test statistics F is in rejection area, then we reject null hypothesis. Otherwise, we fail to reject it. Regarding this conclusion, it's all around the same. If your test statistics be z-score, z-test, be t-test, and now be f-test is falling in rejection area, then we reject falling in the fail to reject area, then we reject the alternative one. Okay. All right, so here is example, performing a 2-sample F-test. A restaurant manager is designing a system that is intended to decrease the variance of time customers wait before the meals are served. Very important thing for restaurants, right? If the customer get tired of waiting, they can move to next restaurant. Millions of restaurants around. Under the old system, a random sample of 10 customers had variance of 400. Under a new system, a random sample of 21 customers had a variance of 256. Much better, right? More customers, less variance. At alpha equal 0.1, is there enough evidence to convince the manager to switch to the new system? Assume both populations are normally distributed. Okay, so let's remember N1 is 10, variance is 400, N2 is 21, variance is 256. So we need to perform a 2-sample F test. So what do we have? Sigma 1 squared for alpha, which is our claim, right? Because we claim that in the older system, which is represented by sigma 1 squared, is a weighted system is longer than with the new system, which represented by S sigma 2 squared. And indeed, here they weighted 400. What was the measurement? Okay, variance just 400. All right. And for the first one, for old system, and for new system, variance is 256. And this way, so our claim S1 squared is greater than S2 squared, and accordingly null will be less than. Degree of freedom for first one is 9. For the second one, numerator denominator, degree of freedom is equal 20. Okay, so F test is equal S1 squared divided by S2 squared, which is 1.56. So this is our 1.56. And if we go to the table, we also need to find our critical value, right? For alpha equals 0.1, right? It's here 0.1, 10%. For right tail test, we are looking n degree of freedom is 9, goes this way. Degree of freedom is 20, goes this way, and it's gonna be 1.96. So now we compare 1.96 to 1.56, and we get our F is less than our F critical. Therefore, we are going to draw conclusion. We fail to reject null hypothesis, which means and our claim is alternative. That means we reject alternative. If we fail to reject null, then we reject alternative. So, and we are saying, since we reject alternative, that means we need to say, we are using the verbiage support, right? There is enough evidence to convince men to support the new system, right? Meaning there is enough evidence at the 10% significance level to convince the manager to switch to the new system. All right? Here we have our 1.56 test statistics, right? And it's falling in the healthy area. Okay, next example, performing a two-sample F-test. Second example, you want to purchase stock in a company and are deciding between two different stocks. Because the stock's risk can be associated with standard deviation of its daily closing prices, you randomly select samples of the daily closing prices for each stock to obtain the results. At alpha equals 0.5, alpha here we have 0.05, can you conclude 0.05, can we conclude that one of the two stocks is riskier investment? Okay, well, let's see. N2 is 30, so stock A, we have N2 is 30, which means degree of freedom, right? We put 2 is 29, and S2 is 3.5. And for stock B, we have degree of freedom N1, which is going to be degree of freedom 1. It's going to be 30. And S1 is 5.7. Okay, so let's solve it. Because we have 5.72 is greater than 3.52. Here we have 5.7 degree of the S1 squared. No, just the standard deviation, right? It's given standard deviation. Let me figure it out. Is this standard deviation or this is variance? It should be variance. Let me see. Associated with, no, standard deviation. Okay. So, well, the smaller standard deviation will give you the smaller variance, right? Because you're squaring. Okay. So, one is 3.5, one is 5.7. So because 5.72 is greater than 3.52, I guess there was cut on decimal notation. It was 5.7 and 3.5. Now they put 3.52, 5.72. Okay, we'll let it go. Or maybe I'll just clean it, because in here in calculation they use 5.7, 3.5. So let me clean this, since they are using without second decimal. Right? It doesn't allow, so I'll just scratch this. Now, since we have two tail tests, right? Let me see. It's between difference. If we need to find the difference between two stocks, right? If they are same risky or not same risky, right? So therefore it's going to be two-tail test. So here we are going to write down. Let me clean this because it's messing the notation. So it's going to be here sigma 1 squared is equal sigma 2 squared, and sigma 1 squared not equal sigma 2 squared. So how much was our alpha? Let me see, 0.05, which means here it's going to be 0.025. Okay, so degree of freedom, for one case it's 30, another case it's 29. D, F, the denominator. Am I right? 30 and 29. Let's go back and check. Yes, with same sample size 30 and 31. So 29 and 30, we are good. And from here, so we get test statistics, S1 squared divided by S2 squared, right? Which is equal greater variance 5.7 squared and a smaller variance 3.5 squared. We use greater sample size as a numerator, and smaller one we use as a denominator to get the right tail, because everything is positive there. And what do we see here? With 0.025, half of alpha, right? And alpha equals 0.025. Degree of freedom here, this way it's gonna be 29. And this way degree of freedom is gonna be 30. And our critical value is going to be 2 point, let me see, yeah, 2.09. If we compare 2.09 to 2.659, it's gonna fall, it's gonna fall in this area, which rejection area, which means we reject null hypothesis, and that means we fail to reject alternative. And our claim is sigma 1 squared is not equal sigma 2 squared. This is our claim. Alternative one is claim. So if we reject null hypothesis, and which means we fail to reject alternative, we are using that there is enough at the 5% significance level. There is enough evidence to support. Enough evidence is null hypothesis here. It should be here, reject null hypothesis. So enough evidence to reject, to support the claim that one of two stocks is riskier investment. Okay, so moving to next, here is a test on the scientific calculator with statistical operations in there. So this is a graph for F test. Here we have F test, and here we have p-value, sigma 1, sigma 2, and 1 is 1, and here is all information with the alternative. One is the alternative, the other one is null hypothesis, and you get the results. So let's move on. And that's all. So we learn how to do interpretation of F distribution and use the F table to find critical values. By the way, I will place the link to critical value for F table in the comments, okay? and we perform two sample f-tests to compare two variances. In technology, we are going to use Way Anova. Way Anova is using f-test. Okay.